Okay, you see the title, Macroscopic Evolution of Mechanical and Thermal Energy in Harmonic Chain. Please go on, Marielle.
So thanks, Stefano, and thanks for the invitation to talk here. So in fact, yes, my talk will follow a little bit the one of Stefano, who were talking about the harmonic chain with the stochastic noise and periodic and boundary conditions. But I will talk about another case, which gives another macroscopic limit, in fact. So just, let's say, an anecdote. It's like when we were working on this subject, Stefano talked once with Joël, and Joël was aware about some biological result, which was quite recent, in fact, and which was more or less what I'm going to describe. So just to show you what Joël told us, I think it was 2 years ago or 3 years ago, he was aware. So it's about mitochondria, which are, let's say, the reserves of energy in our body and everywhere. And these mitochondria can produce heat, in fact, and they act like radiators. I'm not an expert in biology, but just to let you know. And in some very recent papers, so you see it's 5 years ago, basically, the biologists were quite surprised that, in fact, even if you put these cells into a bath which is maintained at a constant temperature, inside the cell, the temperature might be higher than the bath. So there were some strange behavior for biologists that they observed, and it's the subject of recent publications. And this is what we are also going to observe, but in the harmonic chain of oscillators. So another completely different model. Okay, so the macroscopic model is this one, as Stefano yesterday. So it's a chain of oscillators, so the atoms are connected by springs. And since I'm going to consider only the harmonic case and also the unpinned chain, it's convenient to work with distances instead of positions. So I will always talk about distances Rn and momentum Pn. So these two values are real numbers. It's a one-dimensional chain. In addition to the Hamiltonian dynamics on this atom, there are boundary conditions which are very important. So on each side of the chain, there are temperature bath, which maintain the temperature fixed. And there is also this tension, which will evolve in the microscopic time. So it's not the same as Stefano presented, because here there is no rescaling in time. Okay, it's really the microscopic time here. We will see the equation later so that it will become more clear. And so I'm going to define now the dynamics and the configuration. So there are, in fact, n values of R and n plus 1 values of P. You can also assume that R0 is equal to 0, and you have n plus 1 atoms. Okay, so the total energy of this system is the Hamiltonian given by the sum of kinetic energies and potential energies. So here the system is unpinned, so the potential only depends on the distance. This is why it's more convenient to work with distances. And we also assume that the potential is harmonic, so it's a very simple system because the energy is purely quadratic, and we're going to see a linear dynamic. Okay, so as many of you know, this system is too simple because it has a lot of conservation laws, and in fact, the dynamics is completely linear, so you can solve it by Fourier transforms, and you can prove that each Fourier mode of the energy is traveling. So there is no diffusion, there is a ballistic transport of energy in the system. And this is not what I'm going to talk about, because as Stefano, in the talk of Stefano, we add a stochastic noise, which basically keeps only two conservation laws, the energy and the volume. So we destroy, it is important that we destroy the conservation of momentum. This will make, in fact, the system diffusive, but we keep the energy and the volume. And this is really important because the presence of these two conserved quantities and the boundary conditions will produce, let's say, complex phenomena, which is similar to the one which is observed in mitochondria. So with the production of heat inside the system. Okay, so what is the stochastic noise doing? So you also, I know that some of you are familiar with this noise, but I'm going to describe it again. So of course, we want a noise which preserves Hn and also, in fact, Rn, the volume. So it has to preserve both quantities. And one way to do this is to put random clocks on each atom independently. So these clocks are independent. There are Poisson processes and of the same intensity for each atom. And when the clock of one atom rings, then it changes. This particle, this atom, change its velocity into the opposite sign. So it flips the velocity. If you want, you can understand this as random collisions with the external particles if you want, but it's really at random times the particle decides to change direction. And this noise has the great advantage to break a lot of conservation laws, in particular the sum of Pn, and it still conserves the energy, the volume, and basically these are the only conserved quantities. Okay, so now let me write the final dynamics, because this is the most important thing of this talk, I would say. So the final dynamics is, in the bulk, you have an Hamiltonian dynamics, and since we know already that we are expecting diffusive behavior, I'm already writing the equation in diffusive time scale. And so you see that on each Pen, there is the flip acting with an intensity gamma, and also the Poisson processes are rescaled in the diffusive time scale, of course. So both dynamics play the same role in the same time scale. Okay, and we had boundary condition. So the boundary conditions can be written as follows. So on the P0, there is, so first you have only R1 here. This means that you consider that R0 is equal to 0. You have the flip as for any other Pn, but you add also a thermostat which fixes the temperature. In fact, this fixes the average of P0 squared to be T minus. So you have a parameter here, which is T minus, which is the value of the temperature. You could also have had another parameter, let's say gamma prime or sigma, to regulate the intensity of the thermostat, but it's not going to be very important in the result. So let me write it like this. So you have the flip, the thermostat, and on the other side, for Pn, you have the same kind of thing, but now this is like assuming that Rn plus 1 is equal to tau, the tension, which is the force which is acting on the last particle, instead of having a 0 like in the left boundary. And you see that here tau is multiplied by n squared. Okay, so this evolves in the same time scale, the force. And you have also the flip as for each Pn, and that's not the end. So, and we also have the thermostat at temperature T plus on the right particle. So there are two thermostats, one force, and this is exactly how the system of equation can be written. Okay, so this is the starting point. And then we need to solve this and to give a macroscopic behavior of this system. So as usual, so it's quite now well established. So we can use several tools to solve this. So first, this is a Markov process. So we have a generator, and we know that the only conserved quantities are energy and volume, in the sense that we know the equilibrium state. So we have the complete description of the equilibrium state. This is thanks to the stochastic noise. There are Gibbs, and in this case, since we are in the harmonic case, the Gibbs states are really simple because they are products of Gaussians. And now we want to prove a hydrodynamic limit result. So I'm going to, just to simplify, I'm going to state the result in the case where the tension is constant. But in fact, you could also assume that it evolves in time t. It's not a technical, too technical assumption. So you, as in all the hydrodynamic limits, so you make your space rescaling and you assume that there are two profiles at initial time which fit the distribution of distances or the volume, if you want, and the energies. So basically, what you assume at initial time is that the probability distribution on R and P satisfy the local equilibrium property. Here, so you see, this is, I took already the expectation with respect to the initial measure. So this is with respect to mu0n. So we assume basically that you have a, let's say, law of large numbers for the energies and for the distances towards two profiles of energy and volume. So technically, this is not the only assumption. There are, if you want to be very precise and optimal, so you assume these convergences, and you also need to assume moment bounds. So especially of order 1 and 2, so on averages and correlations. But for instance, you can imagine that for the local Gibbs equilibrium state, they are all satisfied. So you can also start from the usual local Gibbs equilibrium state and associate it to the profiles E0 and R0, and they are true. Okay, but we can write general assumptions at initial time, and now we want to understand the behavior of the profiles at later time t. So, and we prove convergences only in terms of averages. Okay, so we look at the average with respect to the law in the trajectory space of this quantity Rn and En, and we prove. So this is the result that we have convergence of the profiles at later time t. So remember that the time scale is already diffusive from the definition of the equations. So they converge to some profile. So the convergence is for fixed t only for the volume, and for the energy it is in L2 also in time and in space, just to be very precise. But what is important now is the equations that we get. So the macroscopic system of equation is this one. So this is the most important thing. So the same diffusive coupled system of equation as if there were no boundary condition. Okay, so this system of equation was already known for periodic boundary conditions, for instance. So we have the diffusive system and we have the boundary condition. So you see that R is fixed at 0 on the left. It is fixed at the tension tau on the right. And the energy is fixed at T minus on the left, and it is fixed at T plus some mechanical energy produced, so due to the tension. So here you see you could in fact make this depend on T, and this is the same equation, exactly the same, which is different in the next slide. Tau is going to be constant. Okay, so it's the Dirichlet boundary conditions on each side. I think that yesterday or the other day, I don't remember, Stefano told about Neumann boundary conditions, maybe, but here it is Dirichlet, both sides, volume and energy. And so what is important to see in this system is the following. So the volume is completely purely diffusive, uncoupled, and the diffusion coefficient is proportional to 1 over gamma, as we expected, with gamma the intensity of the noise. So if there is no noise, of course there is no diffusion. And in fact, the energy can be written in another way, maybe more physically, which gives more physical intuition. So the energy, in fact, it is the sum of the temperature and some mechanical energy. And I'm going to write now the definition of this mechanical and temperature. So mechanical is only related to R squared. So it's R squared divided by 2, the mechanical energy, macroscopic mechanical energy in the system. And the temperature, so you see here that there is a diffusive part plus some dissipation term, which is the result of the conversion of mechanical energy into thermal energy. So this is how the heat will be higher inside the system, because there is some dissipation of mechanical energy into thermal energy. And to see now even better what do we mean by heating inside the system, you can solve the stationary solutions. So now try to find the stationary solution. So now tau is constant in time, and you solve the coupled equations, PDE coupled system equal to 0 with the boundary conditions, and you find these two profiles for volume and temperature. And this profile of temperature has the maximum, so it is equal to, of course, it should be equal to T minus at x is equal to 0 and T plus at x is equal to 1. Should be the case, but we can also see that it has a maximum, so it is a degree 2 polynomial function in x, and the maximum it is inside 0, 1, as soon as, so there is a condition on the values of T plus, T minus, and tau. So the condition is this one, which means that the force has to be strong enough and bigger than the difference of temperature at the extremities. And here, so there is really a heating inside the system, as it can be seen from only by solving the stationary solution of the system. And we can also yes.
May I ask you a question? Quick question. It means in particular that if the temperatures are equal, any tension will give you a maximum inside the
yes.
Yes.
So
that's like the mitochondria, really.
Yes, this is true. You're right. So then you can compute the stationary current, which is in the wrong sense. So the current, the energy flows from the lower thermostat to the higher thermostat if some condition is also satisfied. So tau plus has to be large enough, but you really can see the current going from the wrong in the wrong sense. Oh yes, it's strange that T minus is bigger than T plus, but anyway. And this is called uphill diffusion in the physical literature. Okay, so this has been proved we proved it with Stefano and Thomas, and I'm just going to give some elements to prove this, because the boundary terms are in fact the most technical parts in this work. So for instance, what you need to do is to estimate with your hands, with hand computations, the order of boundary terms, like for instance, the average of P0, the average of Pn, which has not to be too large. So we need some order estimation. Also, you need some L2 bounds, which has to be of the right order. So for instance, this is only considered with the averages. Sorry, I didn't define. So remember that Pj bar is the expectation of Pj here, and Rj bar is the expectation of Rj. Okay, so this is the kind of bounds that you need to prove. Also, the energy bound has to be proved. This is more standard, the energy bound, which is let's say mu is more the boundary terms to treat. And the most important thing, which was the hardest one, is a kind of equipartition result, if you want. So how the mechanical and thermal energy can be compared in the limit. So you need to prove something like this, that the variance of the mechanical energy when this is centered and the thermal energy compensate in the limit as n goes to infinity. So there are some equipartition result that has to be proved macroscopically. And to prove this, so for instance, for the first 2 points, these 2 points, to prove this estimate, so the point is how, by an analysis of the system of equations satisfied by the averages, which is a bit simpler because you don't have the noise. So this is exactly the kind of equation that you have, an explicit system that you can solve and estimate by hand all boundary terms. And for the energy bound, it is more standard. It's based on an entropy production bound, but so we got inspired by the literature to do this. And the last one is the most tricky part. It is, so we solved it by using Fourier tools and Fourier-Wigner functions. As in the periodic case, in fact, we use the same tools. We need to be careful about the boundary conditions, but the way to do this is to you periodize your configuration. So you do as if they were periodic. You take Fourier transforms and you define the wave function, as in the periodic case. And you write the definition of the Fourier-Wigner distribution, which permits to separate Fourier modes. And this is how basically we prove the equipartition result, because I will just conclude with this. The Wigner, what is important to have in mind is that the Wigner distribution can really be split into two terms, one coming from the mechanical energy and one coming from the thermal energy. And this is how we are really able to see how they interact and to prove the equipartition result, which is the fundamental one to conclude the hydrodynamic limit. And I think that yes, so I'm not giving any detail because it would be too technical, and I'm just giving the references, so two references on this subject with Thomas and Stefano. Thank you for your attention.
Other questions?
Thanks, Marielle, for the nice talk. So my question is for the mitochondria. So it has a mitochondria has molecular motors inside, as ATP fuel. So what is so I don't understand why it is surprising that they keep the temperature higher than the environment.
I don't know.
So it has a heating system. It has motors inside.
We would need to ask a biologist. But I don't know. I think they were not aware about the fact that they can no, because they are maintained at temperature. So okay, I don't know.
Okay, thanks. Don't worry.
They really measure the temperature on the surface of the mitochondria, and it's
yes,
very high, much higher than the normal temperature. So it's clear it's not a non-equilibrium system. Yes. Mm-hmm. Inside the mitochondria, the temperature is lower. Okay, Marielle, are there any questions?
Here.
Yes.
Let me try to understand this. So you split your energy into mechanical and thermal energy, but in principle, this is a definition, a little bit ad hoc that you decided for some reasons, no? But deeper justification that when you go and put a thermometer into the thing, what you really see as temperature is your thermal energy.
So here, what is very simple here is that the mechanical energy is R squared divided by 2, and R is completely independent of the other of the energy. It diffuses independently. So you mean in the harmonic case? You want to
No, I just mean that I understand that for the model it's very convenient to do this separation, and it's true that the thermal energy looks like temperature, but is there any reason why when you put a thermometer into a system, what you measure is what you call thermal energy actually, and not the total energy?
So here there are two. Here there are the kinetic energy and the potential energy. So this is why there are.
Can I say comment? Can I answer? When you put the thermometer, what you are measuring is the energy distributed on the Olla frequency. That is a continuous spectrum. Mm-hmm. The mechanical energy is concentrated on the long waves, delta 0K. You see, the mechanical energy is concentrated on the long waves with a macroscopic energy that moves on a macroscopic scale. The thermal energy is distributed and there are some physicists that the heat is continuous spectrum, work is discrete spectrum. That's the distinction that physicists make between work and heat. Heat is continuous spectrum. When you put the thermometer, you're measuring the continuous spectrum because it's getting in equilibrium with that temperature. Sorry, Marielle.
That's okay.
Okay. Thank you very much. Thank you, Marielle. We thank again.